Alright, so in this video I'm going to talk about the t-test for the water lab. So you're probably wondering, we already have a chi-square test, why do we need a t-test? Well, the chi-square test is not going to apply here because we're not looking at an observed versus an expected, which is what the chi-square test is for. We're looking at the different means. So a t-test is used to determine whether the mean of a population is significantly different from the mean of another population. So as it says here in your notes, by the way, this is on page 21, this is useful if you need to compare the means of a control versus an experimental group. So in the lab that we're doing now, think about for a second what the control is. So the control in this case is the drops with, you guessed it, just water. That is our control that we compare the other experimental groups to, which are soapy water and isopropyl solution. I apologize for the background noise. It is never quiet here. You're just going to have to work through it with me. An excellent place to use a t-test in AP Biology would be in comparing the mean of trichomes in the different fast plant generations from the artificial selection lab. So that is a lab that we will do later on in the year. Hopefully we'll be back in school by the time we're doing this lab. Fingers crossed. But fast plants are just plants that grow fast. And they have what are called trichomes. So you're probably wondering what a trichome is. It's not really relevant. You don't have to know that for this lab, but I'll show you anyway. So trichomes are the little hairy extensions on the outside of plants. So if you look at all these images of these plants, they're very hairy. Those are trichomes. And if you look at this one here, those are some very big trichomes. So imagine if you are an insect that eats plants. And this plant has all these hairy spikes all over it. You're probably not going to eat that plant unless you have adapted to do so. But that kind of lets you know what trichomes are used for in plants. So for our example t-test in your notes, it says our null hypothesis, just like in a chi-square, we're going to have a null hypothesis here. For this test is that the mean number of trichomes in generation 2 is the same as the mean in generation 1. So remember, our alternative hypothesis would be that they are not the same. So if we determine that there is a statistically significant difference between the two means, maybe that tells us that there's something else going on versus just random chance or experimentation error. Okay, so we have two separate example sets of data for generation 1 and generation 2, and you can see there's quite a large difference between the two sets of numbers. Also the mean, so 16 over here would be the standard mean for this set of data, and then 44.7 for this. And so you can see that the standard deviation for generation 2 is very large, 23.6, versus the standard deviation for 9.3. Now, something I want to point out, look how large the standard deviation is here, and look at the diversity or the variance of your numbers. We go from 18 to 56, down to 37, to 22, and way up to 65, 33, 82. So that is an example of a large deviation, whereas over here, the numbers do not deviate quite as much, which is shown in our standard deviation. So moving on, the sample size, which is n for both samples, is equal to 7, and that is just how many numbers we have. So we have 7 numbers, 1, 2, 3, 4, 5, 6, 7. Thus, the complete equation for the t-test is, as shown here. Looks like a lot of fun, but luckily your notes takes you through it step by step. So we want to calculate the mean of each sample population and subtract one from the other. Take the absolute value of this difference. Okay, so our mean for x bar 1 represents mean, so our mean for the first set of data is 16. So 6, that's not a 6, 16 minus our other mean, say 45. 45, subtract those and take the absolute value, so then that gives us negative 29, and we take the absolute value, that gives us just 29. If you don't remember, absolute value basically just takes your number from a negative to a positive. So we have 29, so we're going to have 29 divided by all of this down here. So next step, calculate the standard error. To compute it, calculate the variance, which is the standard deviation squared, or S squared. See right here, there's S squared 1, S squared 2 of each sample, and divide it by the number of measured values in that sample, in sample size. Add these two values and then take the square root. All right, so we come up here to our formula. We see S squared 1 for our first set of data. I just chose this set because it's farthest to the left, divided by N1, which you'll remember is 7, plus S squared 2, which is the variance for this set of data, divided by N2, which is also 7. We have 7 numbers. So we just take the standard deviation and we square it. It's already done it for us. That'll not be the case in the water properties lab, so you'll have to do that yourself. So 9.37 so on squared is 87.9, so we'll say 88. All right, so we'll come down here to our formula and do 88 divided by 7 plus, so 23.64822 squared, it gives us 559.23. So we'll just say 559. 159 divided by 7. Okay, and then it said to divide it by the number of measured values in that sample. So 88 divided by 7, and then 559 divided by 7. And then add these two values together and find square root. So I'm going to come over here to the side just a little bit, zoom in so I have more space. So 88 divided by 7 is, so we have 12.6 plus 79.9, and that is going to be under square root, which is going to be divided into, we had 29. Okay, and so we add 12.6 plus 79.9, and then we square root that. We get, so we end up with 29 divided by 9.6, which then finally gives us 3. So we calculated 3 for our statistic, and then in your notes, it calculates 2.9417. So I just rounded up to the nearest whole number. Then it says to compare the calculated value to the appropriate critical t-value in the table included below. So just like in the chi-square, where we found the critical value, we're going to find the t-value, which also should give you some insight as to why it's called a t-test. All right, so here's table 8, and it's showing you all these critical values. So just like in the chi-square test, we're going to use 0.05. Now the question is, in this case, what is our degrees of freedom? The degrees of freedom are calculated by adding the number of data points in the two groups combined minus 2. So on our situation, we had 7 plus 7, and so that would be minus 2. So 7 plus 7 minus 2 is 12. So our degrees of freedom are 12. So then we just cross-reference like we did before, and you see here our critical value is going to be 2.18. Now, similar to the chi-square test, if the calculated t-value is greater than the appropriate critical t-value, this indicates that you should reject the null hypothesis and that you have enough evidence to support the hypothesis. That means that the means of the two samples are significantly different at the probability value listed. If the calculated t is smaller than the critical value, then you cannot reject the null hypothesis. There is no significant difference. All right, so just like before, if your calculated value is great, then you get to reject the null hypothesis. So that is the same. It's good because that helps us to remember. So our calculated value was 2.9 or 3. So 3 is greater than 2.18. So that means we get to reject the null hypothesis. So this next part of your notes is explaining another way to interpret the t-test, and it's using p-values, probability values. So in this case, we're going to move along the row at 12 degrees of freedom. So 12 degrees of freedom because that is our degrees of freedom. In the water properties lab, your degrees of freedom is another number. So you'll follow that number. So we'll go down to 12 degrees of freedom right here. Change my color to blue. So then it says once you find 12 degrees of freedom, till you find the calculated t-value. So in this example, we calculated 2.9417 or 3. In the water properties lab, that number will be different. So remember that. So 12 here, and so we move. So we're trying to find that calculated t-value. So not here. I'm going to draw lines that I remember. Not here. Not here. Keep going. So 2.6. And then we stop right in around here. So this is where our number would lie, which is between 0.02 and 0.01. So since our number lies there, it is less than 0.05. So remember, and as it says up here in your notes, the p-value of 0.05 means that there is a 5% chance that the difference between the observed and the expected data is a random difference, and a 95% chance that the difference is real and repeatable. In other words, a significant difference. Therefore, if an investigator's p-value is greater than 0.05, he or she would fail to reject the null hypothesis that the difference between the observed results and the expected results is due to random chance and is not significant. In our case, the p-value is less than 0.05. This means that we should reject the null hypothesis, and the differences between the means of the two generations is statistically different. There is less than a 5% chance that the differences between the means is due to chance. So in our example data, since it is less than 0.05, that means that there is less than a 5% chance that the difference between these two means is due to just random error. That means there's something going on that it supports our alternative hypothesis. All right, so that is it, and I hope that helps you in completing the water properties lab.